In this video, we will do the 2 questions in the Unit 5 review about the rational root theorem. So we'll start with question 5, and it asks us to find the solutions for the polynomials using the rational root theorem. And there's a reminder there to try to factor after finding each new solution. So if I want to use the rational root theorem, the very first thing that I have to do is find the possible roots for this polynomial. And the possible roots are the quotient of the p's and q's. So we'll start by finding the p's and q's. The p values are the factors of the constant at the end of my function. The factors of 1 are 1, and that's it. We ignore the sign of the constant at the end. It doesn't matter that it's a negative one because we're about to use all of the positive and negative p's and q's. So we ignore the sign for right now, and we'll use both positive and negative. For the q's are the factors of the leading coefficient. So in this case, the factors of 4, which are 1 and 4 and 2 and 2. So I'll list them 1, 2, and 4. We only have to list each one once. Now that I have my p's and my q's, I can set up my possible roots, which are plus or minus p divided by q. And I'm going to go ahead and write these in set notation. So these are plus or minus the set of p divided by q. My p value is 1, and I'll divide it 1 by all of my q values. 1 over 1. Up next we have 1 over 2. And lastly we have 1 over 4. Now these are rather nice in that they don't really have to be simplified. I could simplify the first number, 1 divided by 1, that's just the number 1, but 1/2 and 1/4 can't be simplified. So in this set of p over q's, I have 6 possible rational roots for my function because each of the numbers, 1, 1/2, and 1/4, could either be positive or negative. So what I have to do is start testing these possible roots one by one until I find a root that works, and it'll work if the test gives me a remainder of 0. And the test is going to be using synthetic division. So I always recommend that when you use synthetic division to test your roots, you start with the smallest, simplest numbers first, and leave testing any fractions or larger numbers until they are the only options left. So the smallest, simplest number is always going to be the number 1. So we will start testing the number 1. And we test it by using synthetic division. I'll test the number 1 in the top left corner, and we'll use the coefficients from our polynomial for the rest of our synthetic division. We want to check to make sure we don't need any placeholders. Our degrees go from 3 to 2 to 1 to 0, so I can go ahead and just take my coefficients as they are. I don't have to put any placeholders. The coefficient of x cubed is 4, the coefficient of x squared is negative 9, coefficient of x is 6, and the coefficient at the end is just the negative 1. Now we're ready to use our synthetic division to divide. We'll bring down our 4, multiply it by the 1 in the top left, add up and down we get negative 5, multiply that by the top left, add up and down we get 1, multiply that by the top left, and wouldn't you know it, our very first test, we have found a remainder of 0, which means that x equals 1 is a solution to this polynomial. Now the original degree of our polynomial is 3, which means there should be 3 solutions. I have found 1, which means there are 2 left. I could keep guessing, or, as it's suggested, and as I always recommend, what I should do is look at the polynomial that's left and see if it can be factored, because if I can factor it, I can find the last 2 solutions much easier. So I'm going to go ahead and try to factor this polynomial, but I'm going to have to see what the polynomial is before I can factor it. So the 4 that I have here is the coefficient of my new polynomial. That's 1 degree lower than what I started with, which means it's going to be the coefficient of x squared. Then I'll have negative 5x and a plus 1 at the end. This polynomial can be factored. If I'm going to factor it, I'm going to go ahead and use fake factoring, which starts by multiplying a by c. When I multiply a by c, it will give me the value to put inside my t-chart. So 4 times 1 is 4. So I'll have to find 2 things that multiply to 4 that add to the negative 5 in the middle. That part won't change. The factors of 4 that will combine to 5 are 1 and 4. And if I want a negative 5, they both have to be negative. So I'm ready to put them inside my parentheses. But fake factoring also says that I have to put ax in both of my parentheses as well. So if a is 4, I have to put 4x in both parentheses. Then I can use the factors I just found. Oh, one of these is a 4. So the -1 and the -4 that I found as factors. Now, the last thing I have to do for fake factoring is take the extra 4 back out, because this set of factors is 4 times too big. I have to divide it by 4. The side that's divisible by 4 is here on the right, so I'm going to go ahead and divide both of those terms by 4. So my final factored form will be 4x minus 1. And on the right, we're going to divide 4x by 4. We just get x. And -4 divided by 4 is just -1. Now this is completely factored, which means I can find my last two solutions. All I have to do is set this equal to 0 and solve. If I set 4x minus 1 equal to 0, I can add 1 to both sides and divide by 4. There's my second solution. X equals 1/4, which we can see is one of our original possible solutions, but we didn't have to test it with synthetic division, which is nice. Next, I'll take x minus 1 and set that equal to 0, and I will add 1 to both sides. X is 1. That's my last solution. I have all three of my answers. X equals 1 twice. It's got a multiplicity of 2. And x equals 1/4. Let's take a look at my next rational root question to get a little bit more practice with that. All right. So again, the very first thing that I have to do in order to begin this problem is start a list of my p's and q's. My p's are the factors of the constant at the end, which in this case will have the factors of 1 and 5. My q's are a list of the factors of my leading coefficient, which is 3. So my factors are 1 and 3. Up next, we just have to make our list of possible rational roots by finding the plus or minus p over q's. I'll do this in set notation. So we'll start with my p value of 1, and we'll divide it by the q value 1. And then we'll take the same 1 and divide it by the q value 3. Now I have divided 1 by all of my q values, which means I can move on to my p value of 5 and divide that by 1. And last but not least, we'll take the same 5 and divide it by the q value of 3. These are all of my possible p's and q's. There's not much to really simplify. This 1 over 1 can be simplified just to the number 1. This 5 over 1 can be simplified to the number 5. But other than that, these are pretty much done, which means I now have 8 possible rational solutions. Positive and -1, positive and -1/3, positive and -5, and positive and -5/3. Like I said before, you should always test the smallest, simplest number first. The smallest, simplest number will always be 1. If it works, great. If it doesn't, then you keep going to other roots. So we'll test the number 1, and we'll take the coefficients of my polynomial. We have degree 4, degree 3, degree 2, degree 1, and degree 0. So we're not missing anything. So we'll take our coefficient of 3, -10, -24, -6, and 5. Please remember to use negatives when appropriate. We'll go ahead and divide by bringing down our leading coefficient, multiplying it by the top left corner, we get a 3. When we add up and down, we get 7. Multiplied by 1, we get a 7. -24, -7. -24 minus 7 is -31. Times 1 is -31. We get -37, and when I multiply that over here, -37 plus 5 is -32. Now we're looking for a remainder of 0. We have a remainder of -32, so this doesn't work, which means we're going to have to test a different value. We tested +1. A lot of people move on to other numbers, but please remember that you have positive and negative solutions, and -1 is your next easiest number to try. So that should be the next number that you test. So this time, we're going to test the number -1 with the same coefficients. 3, -10, -24, -6, and -5. Let's go ahead and test this again and see if this time it gives us a value that will work. This time, let's see what we have. We bring down our 3, multiply it by -1, we get -3. Add up and down, we get negative 13. Times negative 1 is positive 13. When we add up and down this time, we get negative 11. Multiply that by negative 1, we get positive 11. Minus 6, we get positive 5. Times negative 1 is negative 5. Oh, I wrote my math wrong. I was like, this should work. What happened? I made a mistake here. This is supposed to be a positive 5. If you look back up here, this is a positive. That was my mistake. Now, when we add up and down, we get a remainder of 0. So this negative 1 does work. Please watch your signs, because as you can see, it's very easy to make a mistake in your signs. So we get a remainder of 0, and that's a great sign. It means that x equals negative 1 is a solution to this polynomial. But this polynomial is to the 4th power, which means we should have 3 more solutions. Now, we could get solutions from the polynomial that's resulting if we can factor it. Let's go ahead and write it out. Remember, this 3 in front is the coefficient of an x that's 1 power lower than our original, so this would be 3x cubed, minus 13x squared, minus 11x plus 5. I could try to factor this using grouping, but if I do, we'll find out that all of the numbers inside this polynomial are prime. There's no way to factor them to make these groups match, so factoring by grouping doesn't work. We use P's and Q's to guess what the possible roots might be if we can't factor. So if we get a new polynomial that can be factored, we don't have to guess anymore. But if our new polynomial can't be factored, we have to keep guessing. So in this case, my new polynomial cannot be factored, so we do have to keep guessing. And when we keep guessing, the best idea is to guess the same value again, because I could have a higher multiplicity. So what I'm going to do is I'm going to use this polynomial, these coefficients, and I'm going to test the number negative 1 again. So here's my negative 1, and I'll take the coefficients I just had, 3, negative 13, negative 11, and 5, and we will test these again to see if negative 1 fits into this polynomial a second time. We'll bring down the number 3, multiply it by negative 1, we get negative 3. Add up and down, we get negative 16. When I multiply that by negative 1, I get positive 16. If I add up and down, I'll get a positive 5. And when I multiply it by negative 1, I'll get a negative 5, which gives me a remainder of 0, which means x equals negative 1 worked in my polynomial a second time. X equals negative 1 again. So that had a multiplicity of at least 2. Now before I go guessing again and you're trying to divide by this negative 1 a third time, I should again check my polynomial to see if it can be factored. So my new polynomial is 3x squared, remember it's 1 degree lower than what I started with, minus 16x plus 5. It may not look at first glance like this can be factored, but if I use fake factoring, I'll be able to find my last solutions. So for fake factoring, again, we multiply a by c, and this number, in this case 15, is the number I put into my t-chart, and I try to add it to the number in the middle, which is negative 16. The factors of 15 that combine to 16 are 15 and 1, and if it's going to give us a negative 16, they both have to be negative. Then all we have to do is put AC in both parentheses, so 3x and 3x, and then we use the negative 15 and the negative 1 from factoring. Now this is a times too big, so we have to divide it by the extra 3, which gives us the factors 3x minus 1, that one won't change, and the left side is divisible by 3. We'll take 3x divided by 3, that's just x, and 15 divided by 3 is 5. This is now completely factored. All we have to do is set it equal to 0 for our final solutions. So if x minus 5 equals 0, x is going to be the number 5. So that's our third solution. And our last solution comes from taking 3x minus 1, setting it equal to 0. If I add 1 to both sides, 3x is 1. If I divide both sides by 3, x equals 1/3. So we found our last two solutions by factoring. And you'll see that they were both part of our possible rational roots, 5 and 1/3. but I didn't have to test them using synthetic division. They came from factoring. It was a little bit easier. All right, in the next video, we will take a look at operations with rational expressions.